طيب بسم الله الرحمن الرحيم. So we started talking last time about the multipath propagation, and then we discussed the multiplexing schemes starting from TDM and FDM, and then the last thing we talked about is cognitive radio and software-defined radio or smart radio access, where we can using software we can control all the radio parameters in software. Hence, we can do all kind of smart radio access by changing these parameters to optimize the performance for secondary user who is trying to access the spectrum without paying, while the primary user is not actually using the spectrum. So last, and this is of course facilitated through the concept of software-defined radio, and the most important platform that we talked about is the GNU radio using the hardware platform called Universal Software Radio Peripheral, which was done, which is currently being developed by NI, National Instrument. This is the most common hardware platform that facilitates this. So most of the radio configuration and processing will happen at the software level, and we only have at the transmitter side, we have D2A, digital to analog, and then from the receiver side, we have analog to digital, and then all the rest is software. So only these two parts are hardware. The rest is all software. Of course, this will put some limitation on the speed that we can reach. Currently, the speed, I think, is, using this particular platform, I think the maximum speed is like 10 megabits per second or 100 megabits per second, not more than that. But of course, the idea is that, like there is very fast processing that we can leverage in order to increase the speed, but the gain on the other side is the smart radio configuration. The last multiplexing paradigm is code multiplexing. As we have discussed before, the best way to understand code multiplexing is by imagining a conversation that's happening between two pairs of users or entities, whereas they are talking different languages, such that these languages, they have absolutely no correlation with each other. Like, for example, Arabic and Chinese or something like this. So if we imagine that a transmitter and a receiver and another transmitter and another receiver, that they are sending data, but this data is not correlated, chances are the receiver can actually distinguish between these different signals, even if they are sending at the same time on the same frequency. But the signal itself needs to have no correlation between each other. And the way to do this is by designing what we call orthogonal codes. Using the orthogonal codes, basically what happens is just to imagine this efficiently. So by multiplexing here, we mean that we have multiple users. User 1 has signal 1, user 2 has signal 2, user n has signal n. Okay? So each of these users, they have these signals, and in order to have one receiver to be able to distinguish between all these signals, what will happen at the transmitter side, we have to do like convolution, or we have to multiply this signal by code 1, and this by code 2, and this is by code n. Right? If we do this, essentially what we get at the shared medium is actually S1 C1 plus S2 C2 plus SN CN. Okay? So if the receiver understands only Chinese, he will be able to extract Chinese from all this composite signal. How? Chinese has code 1, for example. So he will multiply this composite signal by code 1. So if you multiply code 1 by this composite signal, code 1 has very high correlation with itself. So the end result will be S1 times very high number, very amplifying number. Okay? And then the multiplication of C1 by C2 is 0. And C1 by Cn is 0. So these will be cancelled. And you will end up with only this. If you use Cn, then you will extract Sn, and so on. So this is the idea. So that's another way of multiplexing multiple data from multiple users. So somebody might argue that, also we have to divide the environment into codes. This type of technology, of course, is used as part of which generation, as we said before? 3G, بالضبط. So 3G uses code multiplexing, and CDMA in general, or code division multiple access. So this is actually based on the fact that these codes are essentially uncorrelated, and based on the fact that this code has like very, very large dimension. So in a certain environment, I can divide this environment in the frequency domain, or using FDM يعني, into limited number of frequency ranges, صح? And I have to have guard bands between them. صح كده? So if I divide this using codes, the good news is I have very, very large domain of codes in this same area. So I can have hundreds or maybe thousands of codes in this area, which means I can squeeze and I can multiplex thousands of users' data in one particular area, which means that I can achieve very high spectral efficiency. And that was the biggest motivation towards 3G. Of course, that doesn't come with no cost. There's no free lunch, okay? So we need to discuss about what are the pros and cons of this particular multiplexing scheme. This is clear, huh? Okay. So now all channels use the same spectrum at the same time. So these codes, by the way, they allow us to spread the signal from each user on the entire spectrum. That's why they call it spread spectrum technology. Okay, they use what we call this is called spread spectrum technology. So these codes, they actually spread the spectrum of one signal to use the entire spectrum. So unlike FDM, where the spectrum itself is divided in the frequency domain into frequency ranges, here I actually spread the signals to span the entire spectrum. However, each signal will be multiplied by the code, as we said, and because of the orthogonality of these codes, I can still distinguish the signals from each other, even they are sent at the same spectrum, at the same frequency range, at the same time, okay, using the orthogonality theorem. So with that, so it's bandwidth efficient, because somebody might argue that, okay, so it's similar to dividing the spectrum into frequency ranges. So I'm dividing the spectrum using codes. Yes, but the idea here is that the code domain is very large. The code domain is very, very large, right? So there is like some mathematical derivations and proofs and stuff like that we can use something called Hamming codes and so on, that we can design these codes in the size of thousands of these codes in one geographical area, which means I can really multiplex thousands of user data in one geographical area. So in that case, bandwidth efficiency, of course, high, because the spectral efficiency is high. No coordination. This is I tend to disagree with this. There is some kind of coordination here. What this tries to say is that there's no coordination because I have plenty of codes, so I don't really have to coordinate who will take which code, because I have very large domain of codes, so I have multiple degrees of freedom to have whatever code I want, which means that the coordination and the management of these codes is none. But of course, it's not none. It is not. It's less complex because I have large domain of codes, but it's not nullified. It's not eliminated yet, or it's not negligible. There is some kind of coordination already there. It's good protection against interference. Why? Because of course, with frequency domains and with time domains, and any little bit of noise can affect the signal. Here, all the signals are superimposed on each other, and because of the orthogonality, the correlation between these signals is actually very far. So there is no correlation whatsoever. So the noise effect will be low. Okay. So there is high level of protection against noise and interference. Of course, even tapping as well, which has to do with security. So I cannot read data because the data is now coded. So this has, like, some people, they actually say that this is similar to encryption because the signal will be coded, right, or encoded. So encoding means that it's similar to encryption. So there is also, so whoever does not have the code to extract this signal will not be able to tap. So it's like a key. So it's implicitly like a key. So these are all good advantages, but let's see the disadvantages now. That's very interesting. Synchronization is needed. So here we say no synchronization necessary, but here we say synchronization is needed. So no synchronization is related to coordination. Synchronization, yeah, but by synchronization is needed here, we mean the different thing. We mean that, so if I want to send, like, for example, just one bit, right? So what happens is that I multiply this by C1. By C1 is like, signal is like this. Okay, it's just a digital signal. So this one becomes a signal like this. Okay, so this is now the S1 times C1. Okay, so this digital signal at the receiver side, we said the receiver side will need to have a C1 as well, right? But this C1 needs to be synchronized with this C1, which means that the receiver side, the signal should be identical and synchronized. Because as you can imagine, if this signal is not in sync with this, then the zero correlation that we hope for, okay, will not happen as we expect. And actually, the high correlation between the code and itself will also not happen as we wish, right? So you may have no correlation between the code and itself because this is a different code, because it's out of sync. Since this code is out of sync, this essentially means that it's a different code. So multiplying this code by itself with a small shift, okay, might lead to very low value or very low correlation, which will cause a very drastic effect to the signal. Okay, so here the synchronization is needed between the generated code at the sender and the generated code at the receiver. That's what we mean by synchronization here. If we imagine بقى, طبعا in some cases or in some cellular systems, the node can actually have, or the communication might happen in a multi-hop fashion. Okay, by multi-hop fashion I mean like it goes to the base station or to another node, and this node will have to regenerate the signal and send it to another node and so on. This node in that case becomes very complex because now it has to deal with different codes from here and here. So a node might have to deal with different codes for signal regeneration. That's why it says a more complex signal regeneration. Because a node, intermediate node that facilitates the multi-hop communication, it needs to regenerate the signal, okay? Because it has to convert it from analog to digital and then process it, and then from digital to analog again, By digital, from digital to analog, we'll talk about digital modulation in few minutes, where this is used to actually convert the data from digital to analog, right? So this is called signal regeneration. So from along this process, you have to use different codes, which means that one single node needs to manage multiple codes in order to facilitate this communication, and that increases the complexity. But this also happens in FDM, by the way, because FDM, if we use bardo signal regeneration, we might need to send on 2 different frequency ranges, right? So it's the same, يعني. ماشي. And here is by the near far effect. Near far effect is the biggest issue for CDM. This is very distinct to a CDM that does not happen for the case of FDM and TDM. What happens here is that when we go back to the example, that we have multiple users, okay, S1, S2, S3, and Sn, okay. Here, naturally, these nodes are distant, okay, from the receiver differently, right? So some nodes are very far, some nodes are very close, right? So what is the effect of this? The effect of this is that when we multiply S1 by C1 and S2 by C2 and so on, okay, here what we'll get is S1 received multiplied by C1 received, صح? Plus S2 received multiplied by C2 received, and so on. Because of the path loss effect, right? In some cases, S1 will be attenuated more than S2, right? So this is like, again, if we go back to our example of Arabic and Chinese, right? We said that 2 people are talking Arabic and 2 people are talking Chinese. And we said that, if these 2 conversations are happening, the receiver can distinguish between the 2 languages. But the implicit assumption here is that the volume is pretty much the same. The volume between all the 2 languages is pretty much the same. Imagine that if the Arabic language, they use very high volume, right? And the Chinese is very low. In that case, there will be some interference effect, even with the orthogonal codes, right? Because because in this summation, the composite signal, some components will be negligible compared to the others, right? So the energy for some of these signals will be very low. And then the energy for some of these signals, the received energy, will be very high, right? So in some terms, will be negligible, أصلا. So even if you are trying to extract S1, right? S1 has very low energy, and it becomes like a noise. So the implicit assumption when we say that we deal with the correlation for CDM is that the received energy for these signals will be more or less the same. In that case, the orthogonality and the correlation theorem will apply, right? But in order for us to do this, we have to do some adaptation to the transmission power at the transmitter so that at the receiver we receive the same power level on all nodes. Okay? So that part we don't have to do for FDM and TDM. We don't have to do this because, again, the spectrum range and the frequency range is completely separate, and we can use filters, so they are completely separate. But here, the effect of the near-far phenomena forces us to have to control the transmission power from the transmitter so that at the receiver side we reach to the same, more or less, the same energy level at the receiver side, right? So this is there is a huge amount of research that people have done already for 3G, for power adaptation and so on and so forth, in order to eliminate or to reduce the near-far effect for CDM in particular. تفضل.
Professor, in this scenario, you are assuming multiple senders and one receiver.
Yes, oh, this is what typically happens in practice. A receiver will receive composite signal, and the receiver needs to extract one signal out of this composite signal, right?
But we have the signal when it receives is always much weaker than when it is being sent. So the idea.
True. بس in order for this CDM and the correlation to apply, the level of the received signal should be more or less the same. Otherwise, when we say the multiplication is 0, it will not be exactly the 0. And when we say the multiplication is really high, it will not really be high, right? So in that case, you will get like some very high probability of error. So this near-far effect is very critical for CDM, very, very critical for CDM. And that's why power adaptation is very key for all types of 3G networks, power adaptation. So how can we do this power adaptation? It's not within the scope of the course, of course, but it's, as you can imagine, it is possible. It is possible. So I can, first of all, I can measure the distance between each of these users and the receiver. I can have some distance estimation, and based on that, I can adjust the transmission power based on this distance using some path loss model and so on and so forth. I can do that. And of course, there are tons of techniques to do this. It's not within our scope, but it's possible. So in that case, from the transmitter side, I can adjust the transmission power, okay, to a certain level, and it will be different from one sender to another, so that the composite signal will have the same level of power. تمام كده? Any questions? This is code division multiplexing. Now we'll talk about a different topic, which is digital modulation. Digital modulation here is required for baseband communication, where, of course, the first thing we do is that our data is digital, which means that digital is something like this. Either 1 or 0, right? So the digital signal نفسها, it has certain shape based on the ones and zeros. But of course, we cannot transfer this signal on the actual medium like this. As we said, we cannot do this. On the medium, we have to transfer analog signal, right? So this has to be somehow converted to an analog signal, right? So this is the job of the digital modulation schemes. So the digital modulation schemes transforms the digital data into what we call analog symbols. Okay, a symbol is simply can be perceived as one sine wave, okay, with a specific with certain frequency, right, and certain duration, and certain phase. صح؟ these are the 3 characteristics of any sine wave, اللي هي amplitude and frequency and phase. Okay, so we need to convert this digital data into some form of an analog sine wave. So this is actually, when we do this process, what we essentially do is that we convert the digital data into an analog signal in a specific frequency range, but we have 0 frequency, أو baseband. So this signal is still in the baseband, right? Why do we say this? Because in the baseband communication will happen in what type of medium? In wired network, where we have guided medium, right? So we can have baseband because the medium is actually dedicated, right? We have point to point, and the medium is guided, so we can use baseband communication. An example of this is ADSL, Ethernet, and so on and so forth. Right? Okay, so we have this already. In wireless, can we have baseband? In many cases, no, right? In 99% of the cases, no. So what we could do is that we have to have what we call a broadband communication. So in addition to digital modulation, we have to do analog modulation. By analog modulation here, what we mean is that in addition to converting the digital data into an analog signal in the baseband, we also need to push the signal in the frequency domain in a specific frequency range. Why do we do this? Because in wireless, the entire medium is wireless, and we should actually distinguish the signal by shifting the signal in the frequency range in a specific carrier frequency, right? So this is what we call broadband communication. Again, 99% of the wireless systems, they use broadband communication. So in that case, these types of systems, they use two stages of modulation. They use digital modulation and analog modulation. They need two. So both, by the way, both the digital modulation and the analog modulation, they play on the three fundamental parameters of the signal or the sine wave, which is the amplitude and the phase and the frequency. Okay, both of them they use. That's why we have analog modulation. We have amplitude modulation, frequency modulation, and phase modulation. Right. So we need to talk about in details about the different schemes. So we have amplitude shift keying, frequency shift keying, and phase shift keying. So by keying we mean اللي هو digital modulation. By modulation اللي هو كلمة modulation هنا we mean analog modulation. So these are the schemes for the analog modulation, and these are the schemes for digital modulation. But both of them, as you can see, they play on the three fundamental parameters: amplitude, phase, and frequency. Same thing. Okay, but there is slight difference that we will talk about. ماشي واضح الأمور. Okay, so now talk about so this is the architecture for 99% of the wireless systems, where we get the digital data and then we convert it into analog signal in the using digital modulation, and then after we do this, then we need to load the signal on a specific carrier by using analog modulation. We shift the baseband signal in the broadband range in a specific frequency range. Then when we send this, خلاص, we know that this spectrum is actually our spectrum, and there will be hopefully no interference or minimum interference in this particular spectrum. And then at the receiver side, we do the reverse operation. By synchronization decision here, we mean that we have to synchronization معناها I can use any kind of threshold مثلا to say if the sine wave has an amplitude above this limit, then it's 1. If it's below this limit, then it's noise and the end result is 0. Something like that. Okay. طيب. So now we talk about the different schemes for digital modulation first. So in digital modulation, we have three fundamental or three major techniques, which is the amplitude shift keying and frequency shift keying and phase shift keying. We need to talk about the characteristics of each of these. So, of course, some of you have gone through this already. If you have gone through Network 2, we have explained this before. So, in amplitude shift keying, this is the simplest. It says, okay, so if the data is 1, I will send a sine wave, okay, with the same frequency, right, but with a specific amplitude. Let's say 5 volt, okay, which means that there is a specific power or energy level for this sine wave. If the data is 0, the simplest way is to send a sine wave with the same frequency but amplitude 0, which is 0, right? So this is the simplest form, right? This is very easy. So the transmitter is very, very simple in that case, right? So this is a very important characteristic. The transmitter and the receiver is very simple in that case. It's low bandwidth requirement compared to the others. So in terms of bandwidth, the bandwidth requirement for amplitude shift keying is low, right? And that's why if مثلا on the analog side, مثلا if you look at lower AM radio and FM radio, you will see that in AM it's the bandwidth of the channels is smaller. In FM, the bandwidth of the channel is larger, and we'll talk about why now. However, the main problem of amplitude shift keying is always the susceptibility to noise. Why? Because simple noise can cause the sine wave to attenuate. And as we know, the critical effect of noise is always the attenuation as the signal travels over the air, right? So at certain point of time, this amplitude goes down. So the reception might have very high probability of error, right? Because the amplitude of the signal is attenuating anyway. Okay, so in order for us to minimize this probability of error, what do we do? What can we do?
Like charge the signal again or something.
Hmm?
Same ideas before. You said control the energy.
بالظبط, برافو عليك. So increase the transmission energy. We increase the transmission energy in order to lower the noise effect. This is the only thing we could do, right? So can we do something else? Yes, frequency shift keying is more resistive to noise. Why? Because what we do here is that we send a sine wave with the same amplitude, right, but with different frequency. So the one will be sent using مثلا higher frequency sine wave, and the zero will be represented by lower frequency sine wave. So the amplitude is not it's not in this picture. So if the attenuation happens, it happens to the ones similar to the zero. So there's no distinction between the two. But the issue here is that since you are using high frequency and low frequency, as you can imagine, the frequency ranges will be larger, which means that the bandwidth for the FM is always larger, right? Because there is a big difference now between the frequency representation of the one and the frequency representation of the zero, right? So there has to be different frequency range. The reception quality is really high, and that's why if you listen to FM, you always have reception quality much better than AM. Right? Why? Because again, there is clear distinction now because they are now separated in the frequency range, and they are separated by guard band. The ones and the zeros are separated in the frequency range very far apart. So I can distinguish the one from the zero easily because there is frequency range gap between the one representation and the zero representation.
But the cost is that
The cost is the bandwidth.
limited.
The cost is the large bandwidth now, right? طيب, can I have a frequency resistance, noise resistance, without affecting the bandwidth? That's what phase shift keying tries to do. I will not change the amplitude, I will not change the frequency, I will change the phase. The good benefit of this is that I'm using the same sine wave, okay, but for the zero, all I need to do is just to get the mirror of this. So I change the phase 180 degrees. That's all, right? So it's the same sine wave, same frequency, right? But I'm just using the shift of pi to this, or يعني minus sign, يعني basically. So that's easy because here in that case, the bandwidth, as you can imagine, is less, صح? It's maybe slightly larger compared to AM or ASK, صح? But definitely less than FSK, صح? So this is great. So now I was able to achieve noise resistance because I'm not playing on the amplitude now. Okay, so noise will not be able to affect this signal that much. And remember, we have here, كمان, we have sharp change. The noise cannot affect this sharp change easily, right? So that's good, but it's also bad. There is also a challenge for PSK, and the challenge is that always this discontinuation in the signal causes a problem because in the frequency domain, these sharp changes always lead to a very high frequency component. But these high frequency components, they have to be cut somehow, which means that at the receiver side, sometimes you get some approximation to the signal, and that also leads to some challenges or complexity at the receiver side. That's why the receiver in that case will not use, here, the receiver can use just a threshold. If the sine wave is above certain limit, 1, if the sine wave is above, that's it. The receiver for the FSK can be just a filter, okay? So, a simple filter, right? So if the filter says that the frequency of the sine wave is approximately this, so this is 1. If the frequency is this is 0. So I can do this. In PSK بقى, we use what we call phase locked loop. A phase locked loop tries to, it's a hardware circuit that tries to detect the phase of the signal. In all cases, this discontinuation in the signal always poses some challenge. Although it makes the signal noise resistive, but it also introduces challenge in terms of very high frequency components, right? So that's why بقى in GSM, starting from GSM اللي هو generation 2, right? They try to address, of course, PSK is the most attractive because it's noise resistance without increasing the bandwidth. However, it has this discontinuation problem. So they try to work on this discontinuation problem by introducing what we call minimum shift keying. And the idea here is that the bits are separated into odd or even, and then we use a combination of the frequency and the phase. Okay? We use a combination of the frequency and the phase. So we try to have some frequency separation, but also leverage the phase. هتقولي طب ما ده حل ايه المشكلة اللي حلتها؟ لا. By leveraging the combination of both, we can actually split the bits into odd bits and even bits. So we actually reduce the number of bits by half for each of these substreams, right? And then when we introduce these combinations of frequency and phase, we'll see how, right? Then we can really have 2 bits being represented by a sine wave, okay? Which we can do actually using what we call quadrature phase shift keying or quadrature amplitude modulation. Or we can actually use 4 different frequencies for each of these bit combinations. For 2-bit combination, we have how many combinations? We have 4, right? If we have 2 bits, then 0, 0, 1, 0, 0, 1, 1, 1, صح? So we have 4 combinations. So if we use quadrature frequency keying, then we need 4 different frequencies. Here, what I'm going to show you is that we'll use only 2 frequencies and 2 different phases, and we'll do it combined in such a way that will also get rid of this discontinuation, which is a very nice feature that we want to have, because this discontinuation, as we said, causes some problem at the hardware circuit at the receiver side, right? So this is what we call minimum shift keying. So again, this uses the combination between the frequency and the phase, and then it splits the bits into even bits and odd bits. So the bit stream will be divided into 2 substreams, okay? So this will lead to higher bandwidth efficiency using Gaussian low-pass filter and the Gaussian minimum shift keying, which is used used in GSM. GSM as part of a 2nd generation wireless. So we'll see about how this minimum shift key works. So in the first assignment as well, you will have to implement all these digital modulation schemes and perform some experiments to measure the performance and the resistance to noise of all these techniques using MATLAB. So if you don't have MATLAB, you need to try to set up MATLAB as soon as possible. Okay, so what we will do is that the first step, as we said, so this is step number one. The step number one is to split the data bits into odd and even. So this is a step one. Okay, so which means that if we have here for the odd one, for the odd bits, if we have one, then we have positive signal, right? So this one will span 2 bits. Okay, for the odd bit, so this one will span 2 bits, right? And then after this we have one as well, so we span 2 bits and so on. This is 0, we span 2 bits, and this is 0, we span 2 bits and so on, right? So this is the odd bits. For the even bits, we look at the even bits. Here it's 0, so it's negative signal, and it spans 2 bits and so on. So this is the first step. We have to split the bit stream into 2 sub streams by separating the odd bits and the even bits. Anyone not clear on how this is done? Easy? Okay, so this is the first step. The second step is على طول, is to generate the minimum shift keying signal. We use 2 different frequencies, right? We use the two different frequencies. We have low frequency sine wave and high frequency sine wave, such as here, this is F1 and this is F2. The most important condition here is that F2 equals 2F1. As you can see here, we have 1 full cycle, and here we have half cycle, right? So this frequency is double this. So this is a very important condition. Okay, so this is the FSK part. صح? This is the FSK part. So by doing this, it's similar to FSK, صح? By having 2 different sine waves with 2 different frequencies, this is similar to FSK. What will happen back here is that during the signal generation, what we will do is that in some cases we will take this signal and then we'll take the sign of it, or the minus sign of it. So this is the phase part, right? And by doing the way we do this is simply by saying, okay, so we have odd bit and even bit, right? So which means that we have a combination of 2 bits, right? So here we have 4 combinations. Okay, so we have 4 combinations. So it's either 0, 0, 1, 0, 0, 1, and 1, 1. Okay, so we need 4 combinations as well for the signal representation, right? So 2 of them we have already low frequency, different frequencies, low frequency or high frequency. The other 2 combination we'll get them by taking the minus sign of this. Okay, so for example, if I have 0, 0, I will take the high frequency and I will multiply it by minus. So it's minus. Okay, so it's minus the high frequency. If I have 1 and 0, then I will take the low bil minus. If I have 0, 1, then I take the low with positive, which means I will not multiply it by minus. By minus here means it's shifted by pi, صح? معروفة دي, صح? And then 1, 1, I will take the high positive. Positive معناها as is. I will take the same copy of the signal. So let's apply this. So here, we have, for example, here in the even bits, we have 0, 1. Okay, 0, 1. So 0, 1 here, which means low signal, positive. So I will take the copy of the signal here, صح? And I will take it as is. I will not multiply it by sign. So it becomes like this. Okay, next I will take, this is a 0, 1, صح? So 0, 1, low, positive. So low, positive. So I will take this signal and I will take it as is. So this is the minimum shift keying signal, right? And then here I will take this is 0, 1. So 0, 1, low, positive, and so on. Here, مثلا, I will take 1 and then 1. So 1, 1 becomes high positive, so I'll take the high as is. Okay? What is the observation here? The main observation we notice here is that despite any combinations, you will see that the signal here is continuous. There's no discontinuation at all. Okay? And this is not, by the way, this is يعني bandwidth efficient. Although we are using two frequencies, but we are using two frequencies to represent 4 different bit combinations, right? So this is still bandwidth efficient, okay? Because if we try to do the same using frequency shift keying, then we need actually 4 frequencies, which means the bandwidth will be even larger, right? But here we're using only 2 frequencies, and we're using the phase, and the combination between the frequency and the phase allows us to make or to guarantee that the signal is continuous. The main condition here is that this condition is that 1 is double in terms of frequency, right? So you have high frequency and low frequency such a way that F2 equals double F1. Any question?
In the case of 1, 0.
Mm-hmm. 1, 0, right. Low, same.
Yeah.
Yes.
And we take exactly the same.
The same here. This is the low frequency,
yes.
right? We take it the same.
Yeah, but what about if you multiply it by minus?
We'll take the mirror of it, yes. But if you apply any combination, you will notice that the signal will always be continuous. Try all the combinations, you will find that the signal is always continuous. You will not have this discontinuation. Okay? Any questions? So this is all good. So we know now minimum shift keying. This is the technology that's used for digital modulation in second generation wireless. Of course, we have to add, of course, on top of this, the analog modulation. Of course, we know that. But for digital modulation, minimum shift keying looks very attractive. The idea is that we're trying to be bandwidth efficient. So why not increase the modulation level? Or in other words, we can use 4 different amplitudes to represent the 2 bits or the 4-bit combinations. We can do that. So why not 8? Why not 16? Okay. Why not 32? Where do we stop? Okay. So let's see. Let's analyze this. So we have binary phase shift keying, مثلا. For binary phase shift keying, what we do now is that we represent the only 1 bit. 1 bit, we have 2 combinations. We have 0 and the 1. So 0 will be phase of 0, and the 1 will be phase of pi, or 180 degrees. So if we use the IQ diagram, remember the IQ diagram that we talked about? This is the IQ diagram for the binary phase shift keying. We have only 2 symbols. 2 symbols. It's the same sine wave. It's either the sine wave positive to represent the 0, or sine wave negative to represent the 1. That's it. Okay. So this is the IQ diagram for the binary phase shift keying. But why not we use a quadrature shift keying, right? By quadrature shift keying is that we have now a sine wave of phase 0 to represent not the 0, 0, 0. Okay, and then a sine wave with مثلا phase shift of pi over 2 بدل بقى pi over 2. Okay, to represent مثلا 0, 1, and another sine wave with a phase shift of pi to represent 1, 0, and another sine wave of phase مثلا 2 pi over 3. Okay, so this is مثلا or the pi over 4, and then 3 pi over 4, and so on. Same thing, على فكرة. So we can even make it start from here, 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 here. The idea is that the 4 symbols, they will have some phase difference. This is the main thing. And they will be, of course, organized homogeneously in the IQ diagram. There's no point of having 2 symbols close to each other and the other 2 symbols are far from each other. Of course, that doesn't make any sense. So we have to divide the IQ diagram homogeneously for the 2 pi phase. Okay? Any confusion? Okay? So why do we do this? Why do we do quadrature phase shift keying? The idea here is that, of course, by doing this, we can increase the spectral efficiency. we can increase the spectral efficiency. Okay?
It's from one signal.
Right. So, because this means that we can squeeze more bits in the same sine wave, right? So this means that in the same frequency range, I can squeeze more bits. And instead of representing 1 bit, now I'm representing 2. So the spectral efficiency is double. ماشي? So in network 2, if you remember, we used to give you like the symbol rate, or in other words, yani the frequency requirement for the analog signal is equal to, if you remember, there's C, there's N, there's 1 over R, where R is the ratio between the signal elements and the data elements. And here R is 2, which means that the bandwidth requirement for the quadrature shift keying is actually half the PBSK. Okay, طيب, which is really good. But what is the cost here? There's no free lunch. What is the cost here? No. ما طبعا discontinuity exists anyway, سواء في البي بي اس كي او الكيو بي اس كي. All the PSK they suffer from discontinuation. لا ام اس كي لا طبعا هنا خلاص احنا الام اس كي we talked about it خلاص we talked about it.
Maybe at the receiver how to filter this is the cost.
We don't filter here. We use phase locked loop for phase shift key. We use phase locked loops. Okay. لا same frequency. احنا بنقول ما same frequency. لا same frequency. So if R is 2 معناها ايه؟ إنه each 2 bits are represented using one symbol. So R here is 2, which means that essentially the bit rate I can represent using the same bandwidth is actually double. صح? Which is really nice. But there is a cost. Is بقى الكوست. Resistant to noise will start to shrink. Why? Because here, remember, it's the same IQ diagram. You are dividing this IQ diagram on 4 symbols as opposed to 2 symbols. So here, the distance between the 1 and the 0 is definitely large, but here the distance start to get a little bit smaller. Okay? طبعا this will become even more vivid and more clear if we're talking about 8 PSK. By 8 PSK,
We'll divide the 2 by over 8.
yes. So we have 2 symbols here, 2 symbols here, 2 symbols here, 2 symbols here. And for PSK, we're using the same amplitude, which means it's a circle, right? So for 8 PSK, as you can imagine, the distance between the symbols, they will start to get smaller and smaller. So the subjectivity to noise will start to get clearer and clearer, because any noise now will affect one symbol to go closer to the other, and you will have no way to distinguish one symbol from the other, right? Because the noise also affects the phase a little bit, because the noise has it's like this, right? So it does some effect. The first thing it does, of course, it affects the amplitude more than the phase, but it has some effect on the phase and some effect on the frequency as well, right? So by changing the phase even slightly for higher orders of PSK, you will start to have a higher probability of error.
Actually, that's what I meant when I said by filtering the signal. I meant
yes. لا, but filtering is different. Filtering معناها I have different frequencies. I'm using filter to filter one signal from the other. واضح كده؟ So BPSK, going back here. So BPSK is very simple. So the transmitter implementation is very simple. ماشي? And it's robust, is used in satellite systems, especially for large distances. We'll talk about why. Quadrature phase shift keying, here, each 2 bits will be coded into one symbol, which means that I can double the bit rate using the same frequency range, which is good. However, again, the noise resistance becomes an issue. The good news is we'll drive now the probability of error for BPSK and QPSK. And you will see that QPSK tends to have similar probability of error for special types of طبعا Gaussian channel. We'll talk about this, like the BPSK, which is good, but starting from higher modulations like 8 PSK or 16 PSK, لا خلاص يعني definitely the probability of error will be very high. ماشي؟ طيب. Yes. طيب. What will happen بقى for as part of the receiver? What will happen? One also يعني disadvantage for all the phase shift keying يعني signals is like, in order for us to estimate the phase of the incoming signal, we usually use a reference sine wave with a phase of 0. So the phase locked loop will have to use a reference signal, right? Like a sine wave with phase 0, okay? In order to estimate, and then it compares the incoming signal with this reference signal, okay? And based on that, it takes the difference, and then from the difference, it estimates roughly the phase shift, right? So that's how it works. So the idea for the phase lock loop to work efficiently is that the generation of this reference signal has to synchronize with the incoming signal. Okay? So in order to have efficient reception, so this is also a source of error. So the reference signal has to be in sync with the incoming signal, right? Which means that the boundaries of all these combinations have to be done carefully. So the boundaries of the different bit representation have to be done very carefully, right? Because if there is any misalignment, then the estimation of the phase in the receiver side will not work efficiently, right? So the normal PSK techniques, all types of PSK techniques, whether we're talking about BPSK, 8 PSK, quadrature phase shift keying, all of them, they need synchronization between the transmitter and the receiver in order to minimize the error, at least at the reception side. Okay? So this is, of course, in addition to the discontinuation issue that we talked about before. So that's another issue. Why we're talking about this issue now? Because for this particular standard, which is a European standard, in Europe, they actually introduced a small difference in the QPSK, okay, to make it efficient and resistive to the synchronization issue. So what will happen is that instead of trying to generate the signal, the reference signal at the receiver side, and guarantee that it's in sync with the incoming signal, we don't do this. What we actually do is that we take the previous signal as a reference signal for the next one. Okay? So in order to estimate the phase of this, we take the reference signal from the previous bit, and then we measure the difference. So I decide whether it's 0, 0, or 0, 1, or 1, 0, or 1, 1, based on the difference between the previous one and the next one, not based on the difference between this one and a reference signal which is generated at the receiver. I don't have to generate anything at the receiver. So this simplifies the complexity at the receiver side, right? And it does not require perfect synchronization. So this is what we call differential quadrature phase shift keying. Differential quadrature shift keying. So the only difference here is that this does not require a reference signal at the receiver side. Instead, it takes the difference in phase between the previous signal and the current signal. Okay? So by doing this, I don't need synchronization. طب what is the cost بقى? What is the implication of this? اللي هيقولها لي يبقى استاذ. What is the implication of this? طبعا الريسيفر is simpler, slightly simpler in terms of implementation. I don't need to generate a reference signal, which is good. ماشي? But what will happen here بقى? What is the cost of this? So في الحالة الأولانية, in the first case, I have to generate a reference signal, okay? Assuming that I can synchronize perfectly, right? What if there is any error? If there is any error, the effect will be on this particular combination only. يعني instead of saying that this is 1 0, now it's 0 1 مثلا, okay? But what is the impact of this on the next combination? There's no impact whatsoever, right? So any error that will be localized for this. Because in the next bit combination, I will have to generate another reference signal. I will have to do the same. And then the error in one bit combination has nothing to do with the error in the next bit combination. So, what is the in this case, what will happen? There is the phenomena of what we call a error propagation.
Error continue.
Yes, if there is any error, because if this has an error, it affects the next one and in the next one, because the next one is based on the previous one, right? So if there is any error in estimating this signal, the error will propagate in all the bits after this, right? And in order to get back to correct estimation, you will have a very large set of bits in error before you can sync back. Okay? Complicated? ولا things are okay? Okay. So this is done in this particular standard, this European standard. We don't have to memorize this, But at least we know that GSM uses MSK. It does not use any of these technologies. It uses MSK with these particular features that we talked about. There's no discontinuation, bandwidth efficient, طبعا, okay. So and it uses a combination between FSK and PSK. Okay. طب this estimation بقى we need okay, so now بقى we need to analyze the probability of error for BBSK and QPSK. What is the idea behind this? So normally احنا, as we said, for BPSK in the IQ diagram we have two symbols, one with a frequency with a phase shift of 0 and amplitude A, right? So you have certain amplitude for the signal. By the way, if the signal has certain amplitude of A, what is the power? The power of this is A squared. On average, the power will be A squared. Type. If the signal has amplitude minus A, still يعني نفس الباور, ولكن with a phase shift of pi. So this is at the transmitter level. So if the data is 0, we send this signal. If the data is 1, we send the other signal. Okay. What we receive on the other side is not idealistic like this. What we receive on the other side is the same signal, but with some introduced noise. And the noise will cause some amplitude difference, and in some cases, some phase difference. So you will have something like this. Okay? So this is what you will receive. So now, what is the probability of error? The probability of error هو يعني on average كده statistically يعني how many of these received symbols can I receive in error, given that I have noise with certain characteristics. Certain characteristics برضو احنا we characterize the signal برضو by the average power. The average power for the signal is what we refer to as هي is square the standard deviation اللي هو square sigma يعني sigma square. Okay. So so by increasing the sigma square, essentially what we do is that we cause more symbols to be on this side and on this side, and in that case the phase lock loop at the receiver might be confused, and it may actually receive the positive signal as negative or the negative signal as positive. So what is the probability of this type of error? So in order to analyze this, the first thing we do is that this is the representation of the average wide Gaussian noise. Average wide Gaussian noise is one of the most common models for noise. The noise will have this particular power level, which is the amplitude divided by 2, or N0 divided by 2, basically. Yeah. So N0 divided by 2 equals to the sigma square. And the average value is 0, which means that the noise can go positive or negative, and the average is 0, and the average power is sigma square. طب what is the probability density function? This is a little bit from statistics, but the probability density function for the average wide Gaussian noise looks like this. This is the Gaussian distribution, the very famous Gaussian distribution. So it looks, statistically, it looks like this. Okay, and this is the standard deviation. Okay, so by having wide standard deviation, this means that the noise will start to have more effect, which means the sigma square will be high, and this will affect the signal more and will cause more shifts to the symbols, and this will affect the probability of error at the receiver side. So we want to quantify this. Given the fact that the channel has average wide Gaussian effect using this probability distribution, what is the probability of error? So in order to calculate this, we need to know that basically, what is the probability, the probability of error, or the bit error rate, or let's call it probability of error. The probability of error can be calculated as follows. It's actually the probability of sending a specific symbol. Let's say that the probability that the signal is, let's say, 0. Okay. While the noise has a value, which is n0, n value. If I'm here, and the noise has a value which is less than minus a, which means that if the signal is here and the noise has a value of minus a, it will take the signal all the way to here, right? So this means definitely I will have an error. So this is the first case. So by or we mean, in probabilities we mean a plus. Plus if I have a symbol of 1 and the noise is n more than a. So if I'm here and the noise is more than a, then I will get to the other side, which means it's also an error. Okay? There's no other case. There's no other case. Because if I remember here, if I do the phase shift by any means, there will be no. If I change the phase, and it will be on this side. If I change the phase here, it will be on this side, but it will still be the same. There is no error.
It is equal to a.
Yeah, a.
Equal to a.
A noise equal to a. لازم the noise has to be more than a in order for the error to happen. Okay. So, what is the probability of 0 symbol versus 1 symbol?
0 symbol?
Mm-hmm. What is the probability of 0, and what is the probability of having a 0 bit or 1 bit?
0 bit is 0.
Half, 50%, صح? يعني normally on the bit stream
Either
either 0 or 1 يعني we cannot really يعني assume that one is much more than the other صح? It's half. So this is half. And as you can see, because of the symmetry, this is equal to this. صح? So this actually يعني this reduces to a probability of أي symbol, which is sorry half, which is يعني half plus half is 1. So this becomes a probability of noise more than A. This. So this is the probability of error, basically. صح? Because the symbol is half, and the two noise are equal because of the symmetry. So it reduces to probability of the noise greater than A. What is the probability for a probability density function that looks like this? How do we calculate this? This is simply here. صح? The probability that the noise amplitude is more than A, it's from A to all the way to infinity. Okay? The integration of this Gaussian distribution from A all the way to infinity. That's it. We cannot have a closed form solution to this integration. So this integration has no closed form solution. The only way to estimate this integration is by using some empirical يعني, techniques, and we reduce it to what we call Q function. Q function, this is a well-established empirical function in wireless communications, very, very common. And you can only estimate, طبعا, of course, in MATLAB, there is a function. And you will use that in the assignment. So there is a function. There is Q function in MATLAB, already built in. Okay, so it can estimate the probability of error using any. So this is the energy per bit. What is energy per bit? This is actually a square. That's it. Energy per bit. If the bit has an amplitude of A, so the energy per bit is a square. And as we said, here, each symbol is 1 bit, right? So the energy per bit is the energy of the sine wave that represents this bit. It's 1 to 1, صح? It's 1 to 1. So the energy per bit is actually the energy of the sine wave, which is A square, right? And of course, n divided by 2 is in fact the energy of the signal. So this is basically what we call signal to noise ratio, or signal energy to noise energy ratio. So this is basically the square root of the energy per bit divided by the energy of the noise. واضح كده? Which is A squared divided by the energy of the noise. واضحة دي? So the Q function of the square root of the energy per bit divided by the noise energy, this is what we call the bit error rate for BPSK. So this is simple, fairly simple. So in the exact same way, we can drive the one for QPSK. I will not do it. I will not do it completely, but I will give you some hints, and I will leave this as a homework for you. So basically, for the quadrature shift keying, we have let's take the simple case. The simple case is that we have a symbol here, and symbol here, and symbol here. Or you can shift it pi over 4 degrees. It's the same. It's the exact same thing, but we use the 0 phase and pi phase just for simplicity, because everything is pi over 4. It becomes a little bit. So if each of these is A, minus A, and this is minus A. So here, مبدئيا one thing we notice here is that the here بقى, it's slightly different, because in order for a symbol to be received incorrectly, it's not بقى the noise doesn't have to reach to A. The noise here reaches to A بقى. What is this?
The phase between minus A and A.
Yeah, but what is this? احنا بنتكلم احنا the noise has to have certain amplitude for this to happen. Okay? So in order for this error to happen, okay, the noise has to have certain amplitude. What is this amplitude بقى؟ لا مش لا amplitude not phase. amplitude. احنا بنتحكم احنا we control the noise amplitude. Okay? Hmm? ايه تاني؟ Not exactly that. So what is this? This is A. This is A. لا يا شيخ. A square root of 2. صح؟ ما هو ده A square وده A square Euclidean distance. فاكرين الراجل بتاع Euclidean distance؟ فا A و A square plus A square root of كذا يبقى A square A A جذر التربيع الاثنين يعني ماشي A square root of 2. Okay, so this distance is A square root of 2. صح? Which means that in the middle here I will start to have the error. صح? Which means that A divided by A square root of 2. Divided by. Okay? So here بقى I need to estimate when the noise is above this, not above A. The noise has to have. On the other side, what is the energy per bit? That's another trick. All of these are sine waves, صح? Which means that the power level for the sine waves is A square. صح؟ طيب. What is the energy per bit? Pay attention to the definition. It's the energy per bit, not the energy per symbol. So this A node, exactly, lay over 2, because here each symbol represents how many bits? 2. So this is the energy per symbol. So the energy per bit for the QPSK becomes A square over 2. Okay? So if you pay attention to this and this, what is بقى the probability of error? Okay, this is the homework. Of course, given these, it becomes very simple. Very, very simple. Given these two, it becomes very simple. طيب, any questions? The good news is the effect of the noise is the same for PBSK and QPSK. This is very good news because we can now double the spectral efficiency without having to pay anything when it comes to error resistance or noise resistance. That's good. But this is as far as QPSK. That's why the minimum we can use is QPSK. Nobody uses BPSK خلاص. Nobody uses BPSK because we can use QPSK with double the spectral efficiency, so there is no point of using PPSK. ماشي? But we can actually use more than that. تفضل.
I think in the slides, Doctor, there was something you mentioned that PBSK is used for satellite communication.
Yes. Yes, but this is very way maybe in generation 1 ولا حاجة يعني very far يعني way in the past. بس يعني now nobody uses this even for and remember for satellite communication the effect is not Gaussian noise only. There is extreme path loss effect. طبعا path loss effect becomes much more dominant in that case. One thing to also notice here is that, as we said, by increasing the modulation level, right, the noise starts to have a more effect. Okay? But we have much better spectral efficiency. So that also calls for some adaptive modulation, and many people they talked about this, or they did some research on this. They are adaptive modulation techniques. This adaptive modulation techniques tries to change the modulation level based on the channel state. So if I know that the channel state is very noisy or the noise level is high, there's no point of using a 16 PSK مثلا. صح? Because the noise effect is going to be drastic and the probability of error will be very high. So it's better for me to use a QPSK in that case. If I know that the noise level is low, in that case I can increase the modulation level and enjoy the high spectral efficiency. But in order for me to do this, the overhead is I have to know the state of the channel. Is the channel really in deep fading? Is there any noise? Walla, it looks like there's no noise. How can I do this? How can I estimate this? How can I get the channel state? Just send like some pilot signals, and exchange these pilot signals between the transmitter and the receiver, and look at the pilot signal and see how it's affected يعني. ماشي؟ تمام كده؟ So now we said that if we use if we use PSK and then we increase the modulation level, we end up with a circle. And as we increase the modulation level, the circle starts to get more dots, okay? But we can try to be smarter in that case, and we can use, similar to the fact that we use for minimum shift keying, we use the combination between the frequency and the phase. We can actually also play with the combination between the phase and the amplitude. This is what we call quadrature amplitude modulation. Quadrature amplitudes. By quadrature, we mean phase. Amplitude, we mean amplitude. So here we use the combination of the phase and amplitude. By doing this, we can have multiple circles, and we can distribute the symbols in the IQ diagram more homogeneously. Not just stick with one circle, but we can play with the amplitude as well. And this way, in the 16 symbols, I can distribute the 16 symbols now on 2 squares or 3 squares, in which case I start to have a larger distances between the symbols. واضحة دي? So I can distribute the symbols on the IQ diagram and then increase the distances. Increase the distances makes the modulation more resistive to noise. صح? So, and this is the idea of quadrature amplitude modulation. In the assignment as well, you will try the 16 QAM and measure the performance of this. Of course, by doing this, the spectral efficiency will be the same, but the noise resistance will be higher. So in terms of in terms of bandwidth requirements for QAM is similar to same modulation level for PPSK, but this will be more noise resistance. Okay? So the probability of error here will be less. ماشي كده؟ So 16 QAM talks about using one symbol to represent 4 different bits. 4 different bits, because for 4 different bits I have 16 combinations. ماشي كده؟ So the number of bits gives me a combination of 2 to the power the number of bits to know the number of combinations I can have. Any questions? So just by using the combination between amplitude and phase, I can have the same spectral efficiency with lower probability of error. Yeah. Of course, that comes with a little bit of cost on the transmitter and the receiver side in terms of complexity, but the complexity is not that high يعني. ماشي؟ طيب. Now we'll give an introduction بقى على الايه. It's a totally different topic. So now we talked about digital modulation, and we give you some idea about analog modulation. Now we need to talk about the cellular system architecture. So with all these modulation techniques, we can convert the digital data to analog signal, and from the analog signal we use broadband communication to shift the signal in the frequency domain, right, to control the frequency range where the signal will be transmitted. So this is all good. But what is the implication of this on the cell level? Cell level, by cell level, we mean here we have a large city, we have a big city, and now we want to design, okay, how many base stations or cell towers I need to have in order to cover this city. Okay? طيب, so what we could do is that we say, okay, so we have this big city. So one thing we could do is just to say, okay, so let me just have two big cells to cover this entire city, and here I put one base station, and this base station will cover the transmission here, and with this base station will cover the transmission here. والحياة حلوة, and there's no issue. Okay? So what is the implication of this? And if I try to make it a smaller circles, which means I use what they call a small cell design, which means that the city will be covered with more cell towers. Okay? Somebody might argue that, why bother? I can have one big tower, right, to cover half the city or the entire city, and that's it. There is serious implication for this type of design. So we need to compare what is the advantages and disadvantages of each of these design. اللي هو cell structure. Should we have large cell structure or small cell structure, right? So طبعا again going back to this example حتى ممكن حتى نشيل ال by having communication, what we could do here is that we can say that if I have a mobile station here communicating with this cell tower, and I have a mobile node here communicating with this cell tower, what we are essentially doing here is that even if these nodes, they are using the same frequency range, and at the same time, no interference will happen, صح? Here what we are essentially doing is that we're using the space or the spatial diversity. Okay? So by dividing the big city into two cells here, we are trying to use the spatial diversity, right? But for this particular scenario, it might work. But what about this scenario? If I have a node here, which is trying to send to this, and another node here, which is trying to send to this, right? So in that case, we cannot use spatial diversity here, صح? Because these two nodes will send a wireless signal with a transmission range that will go to the other cell, right? So in which case, the two transmissions, if they happen at the same time at the same frequency, they will interfere with each other. Okay? So here there is an issue. So spatial diversity cannot work in all scenarios. So that's why even for the cell structure, we also need to have like some usually we have some frequency planning or code planning. Okay? Usually frequency and code, yeah. ماشي? We have to have some code management or frequency management, which is what we call spectrum management. Yeah. Spectrum management بقى برضو is a big area of research. تمام؟ طيب. So what is بقى the implication or the طبعا GSM promotes the use of small cell structure. Why بقى we need to see the advantages of this, and we need to also talk about the challenges or the disadvantages. So mobile طبعا one thing we should keep in mind while we are discussing this, of course, is that mobile stations cannot have device to device communication. يعني بمعنى they have to communicate through the cell tower. There's no يعني communication that happens directly between devices. This is different technology which uses Bluetooth or Wi-Fi direct. This is different technology, but for cellular communication here, all the communication has to go through the base station, similar to Wi-Fi. Wi-Fi برضو supports going through the access point. So this is what we call infrastructure communication. So any type of, even if the other node is next to me, it has to go through the cell and come back. So this is what's explained here. Mobile stations communicate only via the base stations. They cannot communicate directly to each other, even if they are next to each other. as long as they are using 2G or 3G or 4G or 5G. Cell sizes, they can range from 100 meters all the way to 35K. So 35K requires, of course, high transmission energy, but it's possible. It's possible. Even with mobile devices that uses cellular communication, I can reach to that level. Of course, I have to use very high transmission power, but the signal can still reach that level. And that's usually used in remote areas and urban areas, usually. Because in remote areas and urban areas, usually there is no multipath propagation and there is no obstacles, and الدنيا تبقى يعني very widespread, and there is no actually high density of users. Okay, so the users are very بيسموها ايه very separate and distributed. ماشي, they are not very dense. In big cities, usually the user density is very high. Imagine مثلا people are watching the game in the stadium, so the user density is very high. That usually happens in big cities. But in remote areas and urban areas, usually, or suburban areas, usually the user density is small. So what is the advantages of the small cell structure compared to high cell or large cell structure? The first thing is that it's higher capacity. Why? I can support higher capacity. Why? Because each when I talk about a specific tower, specific base station tower, this base station tower controls a limited amount of resources. What are these resources? Layer radio resources. What are these radio resources? It's the frequency channels or the amplitude, or يعني how can I divide this and use some of the multiplexing techniques? It's limited per tower, per one tower. So one tower has a specific spectrum range, right? And it divides this range whether in the time domain, code domain, or frequency domain, right? But it has limited spectrum. Within limited spectrum, it can have certain capacity. So if I reduce the number of cell towers, so essentially I can increase the capacity. صح? تمام? So that's so by increasing the capacity, I can increase the number of users that can be supported. And that's more clear, especially in big cities where the user density is high. So when the user density is high, I cannot just use one tower to cover the entire city. I cannot do this. So I have to use small cell structure to support very high user density and very high capacity. Also, that has the advantage of low transmission power needed, of course, because of the fact that when we talk about 100 meters, of course, the transmission power needed is much less compared to if I need 35 kilometers. So basically, the transmission power is less for the small cell structure, and that's why we can have مثلا devices like very highly portable like this, because this obviously has some limitation in terms of transmission power. I can reduce the size of these devices and still have good level of communication. It's more robust and decentralized in the sense of the fact that when we have many of these, it's like distributed. So I'm distributing the load of the network on smaller cells. So it's very much decentralized. But of course, this comes also with a cost that we need to talk about. ماشي? طيب. Here also, when I reduce the range of communication, essentially what I'm doing as well is that I'm reducing the probability of interference or the number of interference sources. صح? Because if I talk about a very large distance, okay, when the signal travels from here to here, it suffers from many sources of interference. When I reduce the size of the cell, the interference will be more localized. So I can deal with more localized interference as opposed to many sources of interference as the signal goes through the high distance. ماشي? So these are all very nice advantages which really forces us to have to use the small cell structure. But of course, this comes with a cost. The cost is that, of course, more hardware. So definitely the infrastructure that we need in that case to connect all these base stations will be more complex. But we have to do this. Otherwise, the service quality that we will provide to the users will be very low quality. Okay? So in order to increase the quality of service for the users, we need to have a more dense structure and smaller cell structure. There's no way around it, right? And of course, this will all the hardware implementation side will be multiplied. So more antennas, more switches, more infrastructure. So the hardware infrastructure will become much more complex, and of course the cost will be higher, right? But of course, this all with the objective of trying to provide high quality of service for the users. Another issue, which is handover. Handover becomes very frequent in that case. So imagine if I have small cell structure and there is a car that moves. So in that case, handover here talks about the fact that the car will have to change its association from one cell tower to another, right? So as it moves, it has to change its association. And this by the way, has certain overhead, as we said, because handover requires the fact that you have to hand over the resources from the old cell to the new cell, right? Because you're taking some radio resources from that cell. So if you move to the range of another cell, then you have to release the resources from here and then take the resources from the new one. And you have to do that very frequently, which increases the overhead. Again, all of these, we have been able to mitigate and have sophisticated techniques to get over all these issues. And that's why we have to incur that overhead in order to provide high quality of service to the user. Okay? We know how to deal with all these things. These are, of course, disadvantages, but we know how to deal with them. So now handover techniques are very well established, and frequency planning techniques are very well established. Also, frequency planning is needed. As we said, because cells next to each other, definitely they need to use different frequencies. ماشي? We cannot rely on spatial diversity. So we can say that, okay, so these two small cells, okay, this uses F1 and then this uses F2. Maybe the cell here, ماشي, it can use F2. It may be able to use F2, صح? Okay? But I have to control the transmission power level in order to have complete separation between this cell and this cell. Okay? So what if I have another cell here? Okay? So I may have to have F3 in that case. صح? So what if I have another cell here? So frequency planning here becomes an issue. Okay? So I have to manage the frequency ranges in all these cells. And the more dense they are, the more complex this frequency planning will be. واضح كده? So frequency plan, but again, all these issues are taken care of, right? So we comfortably know how to deal with all these issues. We know how to deal with all these issues, and that's why, in starting from 2D, because we said that handover has been introduced in second generation. If you remember the first lecture, yani, handover has been introduced in second generation with GSM, right? So with handover with GSM, all these issues have become really يعني resolvable. ماشي كده واضح؟ So that's the frequency planning. So we can use some frequency reuse, as we said. So we see here. So this is frequency 1. All the neighboring cells, they have to use different frequency. But maybe from here to here, we can use the same frequency. So we can use by frequency reuse. ماشي? So if space-wise the cells are very, very far apart, only then we can use the same frequency. So frequency reuse only with a certain distance between the base station, and the standard model usually use what we call 7 frequencies. So here we have each cluster of cells, because normally the cells are represented using hexagon. Normally, ماشي? But of course, this is idealistic representation. This is only for modeling. In practice, by the way, the cell may have a very funny shape depending on the يعني the interference level at the boundary side.
The layout of the urban areas.
Yes, and the layout and the obstacles, the structure of the city. So the cells in practice, they have funny shape, but of course we cannot use that funny shape for modeling. We have to use well-established shapes. So normally what we do is that we use hexagon. And why hexagon? Why not circle? Right? Because hexagons, they have a nice property in terms of covering certain area without overlaps. يعني. That's why we use hexagons normally. يعني. ماشي? طيب, another thing is that we can use fixed frequency assignment versus dynamic frequency assignment. By fixed frequency assignment here, we assign frequencies similar to frequency division duplex. Here we assign frequencies, we assign 7 frequencies, and we never change them. We never change these frequencies. خلاص, the assignment is fixed and it's permanent. So certain frequencies are assigned to certain cells, and this is fixed. The problem with this is that, as we said before, the interference is actually frequency selective. So certain frequency levels or certain frequency ranges might have more interference than the other. And this based on the fact that مثلا يعني nowadays, as we all know, 2.4 مثلا gigahertz range is very, very condensed. صح? Because it's free license. So 2.4 is full of interference مثلا. Okay? Versus if we go higher frequency, then the interference will start to get smaller. But if we go higher interference, by the way, remember, we have to increase the transmission power. صح? As we discussed, higher frequency means faster attenuation, so we have to increase the transmission power. So that also has to be taken into consideration. So if we have different interference range, this essentially means different يعني capacity on the cell. ماشي? And also with different user traffic load, it becomes more severe if you have higher interference at certain frequency and low interferences in other frequencies. Dynamic بقى frequency assignment بقى talks about the fact that the assignment itself is dynamic. I may have the same 7 frequencies, but I can change the frequencies depending on the traffic capacity. ماشي? The traffic load يعني from the user. So if I know مثلا إن هو there is deep fading in certain frequency range, but I have high density users in this cell. Okay, so it's better for me to change the frequency planning and assign different frequency to this cell, which means essentially that all the cells around it will have different frequency. So I can rearrange the frequencies depending on the interference level and the traffic load or the user density. So these 2 parameters will allow me to rearrange the frequencies accordingly, to have more capacities in certain cells and lower capacities in other cells. ماشي كده? Any questions? So this is the fixed frequency assignment versus dynamic frequency assignment as part of the frequency planning. Okay, ماشي خلاص. هنا بقى we'll talk about sectorized cells and stuff. We can talk about it next time, inshallah. مش مشكلة. We can stop here.